Hello friends, good afternoon and welcome to our EduSet live lectures. Dear friends, as you know that it is a continuous effort from our side to bring knowledgeable and knowledge-enriched lecture for you every day. In a similar vein, today we are conducting yet another lecture in computer sciences. In today's lecture, we will try and understand hardware description languages. To discuss this topic, we have with us our subject expert, Ms. Veepsa Bhatia. Ms. Bhatia is Assistant Professor in Department of Electronics and Communications Engineering in Indira Gandhi Delhi Technical University for Women. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you. Good afternoon friends. The topic of my lecture today is hardware description languages. Before we go into the modalities of the subject, I would first like to introduce what do we understand by the term hardware description languages. Now, those of you who are familiar with hardware designing in terms of digital domain, like designing of a circuit and then subsequently designing of an entire digital system, we know that later whatever technology we are using and coming up with a digital design has to culminate into a chip. A design that can then be practically used and physically manufactured using certain design techniques. Now, fabricating an IC, fabricating of an integrated circuit, be it digital or analog, is a very costly and a tedious process. So, any error that originates into the circuit will culminate into the fabrication, which will make it very difficult to rectify the error once the fabrication has been completed. Now, coming to the digital circuits, the circuits can be tested once the circuit has been manufactured. If there is a possibility to test the circuit for all kinds of errors generating in terms of the circuit performance, in terms of the logic developed, in terms of the timing consideration, then it will be much easier to take a decision as to the circuit that has been designed is suitable for fabrication or not. This is where the hardware description languages come into picture. As the name suggests, hardware description language stands for a language which has been designed to describe the description of a hardware being designed. Here we are talking specifically about digital circuits and to what level of abstraction we can go, which we will see as we move further into our presentation for the day. Now, hardware description languages essentially is a programming language that is used to describe the behavior or the structure of a digital circuit. HDLs are also used to simulate the circuit and check its response. The circuit can be simulated by giving it the signals similar to the signals expected in the real world, and the timings and the response of the circuit can then be assessed and it can be determined as to when the circuit is going to be physically working, how this is going to function. Now, many HDLs are available for this purpose, most popular ones being VHDL and Verilog. Now, most of the CAD tools available in the market support these languages. Today, we are going to be focusing mainly on VHDL part. Now, basically, talking about HDLs, what role does an HDL specifically play? Now, the role can be divided into three parts. It is used to specify a design, that is, give a design specification, design simulation and design synthesis. By design specification, we mean that unambiguous definition of components, functionality and interfaces can be defined. That is, what is exactly expected, what are the components to be used, the functionality that is expected of the circuits and the interfaces that can be employed in this particular circuit. Now, second is the simulation of design. By simulation, we understand that giving signals similar to the real world signals or the target signals which are expected in when this circuit becomes functional physically. So, that is used to verify the system, the subsystem that is there, the performance and functional correctness prior to actual design implementation on chip. And finally, the synthesis of the design, that is the automated generation of the hardware design. Most of the HDLs that are available, the process becomes a three-step process wherein we write the definition in the HDL language that we are using, be it VHDL or Verilog. They have their own syntax. Using that syntax, we syntactically write the program. Then we simulate the program to see the hardware that has been described using the HDL, whether it is working properly. Once that has been done, this software or the HDL also assists us in the synthesis of the design, that is giving us the hardware the design expected out of this circuit once it becomes goes into the fabrication stage. Now the benefits are tremendous. One of the biggest benefits that is possible is the cost reduction and cost justification. That is, once we have decided to go ahead with the fabrication of a particular digital circuit, we know that we are going to be investing a lot of money in this, and investment can be justified if the circuit has been tested prior to actually going in for hardware fabrication. So that is where HDL offers the most important benefit in terms of digital system design. Besides that, it provides a technological independence, that is, the circuit is portable and it can be reused. The circuit can be taken from one platform to another. Once the circuit description has been given, this can be reused. As a simple example, for example, I am trying to implement a 4-bit full adder. This would be requiring 4 1-bit adders. So once a 1-bit full adder has been designed, it can be reused to come up with the 4-bit adder, which can then further be used to design an ALU and so on. So the reusability of code remains there, and it can be used as and when required. Since it is the code, any changes can be entertained in the code because it is at the stage where it is only being simulated before going ahead with the final fabrication. Then it allows for interoperability between multiple levels of abstraction. That means, as I just mentioned, that level of abstraction can be at the gate level, it can be at the circuit level, or it can be at the system level. For example, I am testing the functionality of an XOR gate, which is at the gate level. Then I can use this XOR gate to develop a full adder, which is at a circuit level, and then using the full adder I can go in for a 4-bit parallel adder or a 4-bit serial adder, which will be the system level. So different levels of abstractions can be supported by the use of HDLs. Furthermore, as I mentioned earlier, the cost reduction is a very important factor, and which becomes quite a critical consideration when going in for system fabrication. Then there is a higher level of abstraction available wherein the details of the program can be hidden, only the results can be made available. So this makes the design task much simpler. The design is less error prone and productivity is increased. Further, the errors that are introduced, for example, I am working on a particular circuit and the simulation results show me a propagation delay being observed at the output. Then while at that level, I can rectify this error without having to bother about it once I have gone with the fabrication, and that is when I am going to encounter this error. So this saves a lot of time and energy before we actually go ahead with the final circuit fabrication. Now HDL, there are three types of HDL coding styles basically. There is a register transfer level style, which is normally called as the RTL. There is a structural style, and there is a behavioral style. These styles are typically found in all the HDLs that exist. More critical modalities, more typical styles are different for different types of HDLs that are there, and as and when we go about studying a particular HDL, those styles become more clear. Now basically, what do you understand by RTL? As I mentioned, it stands for Register Transfer Logic. To model combinational and sequential logic components, normally the RTL technique is used. Only a small subset of the language statements can be mapped into the real silicon. As can be seen from the block diagram, there is an HDL code that is written. This code is translated with the help of a generic technology. The unoptimized generic Boolean netlist that is generated out of this is sent for optimization and mapping, along with area and timing constraints which are fed into it, and the target technology for which this particular RTL description is meant. And finally, we come up with optimized gate level netlist, which is later utilized for the purpose of fabrication of the IC. Now structural level basically describes connectivity between components. So this code consists of basically mapping of the ports. As can be seen in this particular block diagram, there are two boxes which are essentially black boxes which are indicating two components. All we need are the definitions for these two components and how the inputs and outputs are being mapped through these components to generate the final output logic level. For example, talking about a simple full adder, a full adder comprises of XOR gates and some AND gates. So structural level definition would require defining those many number of XOR gates and those many number of AND gates as are required to produce the output, and along with that the ports for inputs that will be the 2 bits to be added and the carry bit, and 2 ports for the output, that is sum and the carry out, have to be defined. Now, behavioral level, as the name indicates the behavior. It describes the behavior, that is functionality and performances that are expected out of the circuit under consideration. All language features can be used in this one, and basically we are not talking about the component level, we are talking about the behavioral level, as if for a full adder, what I am expecting is that the output sum should be given by A XOR B XOR C. So that means I am directly giving the behavior, despite the fact that I know it is going to be requiring an XOR gate, I am not going into the structural details. So I am simply specifying the functional specification and the expected performance out of this particular circuit. Now, there are different levels of abstractions that are encountered when we are discussing the HDLs. The structural level is the lowest level of abstraction. The intermediate level is the RTL level, and the highest level of abstraction is provided by the behavioral type of programming. Besides that, now coming over the abstraction levels again are going to vary depending upon the kind of HDL that I am considering. So today I will be focusing mostly on VHDL, and accordingly the levels of abstractions available in VHDL will be discussed as we move forward. Now, VHDL stands for Very High Speed Integrated Circuit. The VHSIC is normally called hardware description language. So as can be made clear from the abbreviation itself, that this kind of hardware description languages is very well suited for very high speed integrated circuits, making it very popular, because high speed circuitry is the demand of the day, and for those circuits the VHDL language serves as a very good medium between the actual hardware and the circuit design techniques. Now, both VHDL and another popular HDL language, Verilog, are officially endorsed by IEEE, that is Institute of Electrical and Electronics Engineers Standards, and other HDLs besides this VHDL and Verilog, which are oftenly used but not as popular, are the JHDL, that is Java HDL, and proprietary HDLs such as Cypress Semiconductor Corporation's Active HDL. But VHDL and Verilog, being open source, are easily available and are easily portable. So these are the two most popular HDLs being used in the industry today. Now, VHDL can also be used to model a digital system at any level of abstraction, ranging from the algorithmic level to the gate level. Below gate level, VHDL does not work, that is, the transistor level description of the circuit cannot be made using VHDL. We can only begin from the gate level, and from the gate level beyond to the complete algorithmic entire system level can be easily designed using VHDL. Now, the complexity of digital systems being modeled can vary from a simple gate to a complete digital electronic system or anything in between. As I mentioned earlier, I can design a simple gate such as an XOR gate, go in for a circuit such as a full adder, and then go in for an entire system employing this full adder, and many such circuits can be integrated together. Now, digital system can also be described hierarchically. I can begin from describing a bottom-up approach or a top-down approach. Bottom-up approach refers to gate definition, followed by the definition of the system, followed by the circuit, and ultimately followed by the design of the entire system. Or a top-down approach is also possible, whereby the entire system is first defined, then the subparts of the system, that is the circuits, followed by the gates that are to be utilized by the systems, are defined. So the hierarchy is fully supported, be it the top down or the bottom up. Besides that, another very lucrative feature of HDLs is the management of timings. Timings can be explicitly modeled in the same description. I can define as to when I am expecting a particular type of a signal to produce an output, how long I want to wait, what delay I want to introduce, and that timing consideration can very well be incorporated into the HDL description. The output waveforms or the output bit codes generated from VHDL are in coherence with the timing considerations that have been defined into the program by the designer. Now, the level of abstractions have increased over the last few decades. 1970s, the abstraction level was the circuit. 1980s marked the gate level abstraction, followed by RTL level modules in the 1990s, and the year 2000 onwards it has been the system level of abstraction. That is how the complexity of the circuits over the last few decades has increased. So the purpose of the HDL is to cope up with this level of abstraction, to come up with a kind of hardware support that can take care of all these levels of abstraction to the highest level of sophistication available currently in the industry. Now, as can be seen from the diagram, the capability of VHDL is from the system level to the module to the gate and to the beyond the circuit and the device level. This capability diminishes for the VHDL, whereas Verilog is capable of supporting up to the circuit level or the transistor level. Now, coming specifically to the VHDL, VHDL can be described as an amalgamation of 5 different types of languages, those being it's a sequential language. That means it is capable of designing the circuits which are sequentially to be executed one after another. A concurrent language whereby different signal assignment statements can be concurrently handled. A netlist language which generates a netlist upon execution. Timing specification, as I just mentioned, it is able to handle the timing constraints. And waveform generation language, which is going to give me the waveforms which are going to result after some input and the timing specifications and considerations have been applied. So VHDL offers a lot of flexibility to the designer, to the user, to be able to guide the programming as and how it is going to be more suited for his or her circuit. Now VHDL not only defines the syntax, but it also defines very clear simulation semantics for each language constructs. That is, for all of them there are specific semantics that are given besides the syntax which is there for any kind of programming language, be it a computer language or be it a hardware description language. There is a syntax that is defined. Besides that, the semantics for different types of constructs that are used in the language are also very clearly provided by VHDL. Then models written in this language can be verified using a VHDL simulator. So a simulator is provided, so it is very easy that the models that are written that can be easily simulated. However, the language is a strongly typed language and is often verbose to write because it follows its own semantics and syntaxes. So it becomes a little difficult initially to understand, to learn and come to the terms with all the different syntax that is followed in the language. But once understood, it makes the life of a designer much easier. Now, coming back to the history of VHDL, this language was first conceptualized, or its need was first felt in 1981 under the VHSIC program, the Very High Speed Integrated Circuit program. Now, this program was actually initiated by the Department of Defense of the US government, wherein a number of US companies were involved in designing these VHSIC chips for the Department of Defense. So, eventually a team of 3 companies, IBM, Texas Instruments and Intermetrix, they came together and were first awarded the contract by DoD to develop a version of the language in 1983. So version 7.2 of VHDL was then developed and released on to the public in the year 1985. After this release in 1985, there was an increasing need to make this particular language a standard, an industry-wide standard which can be easily adopted, which would later make this language in platform independent and can be used for reusability between different vendors, different technologies. So in order to do that, the language was transferred to IEEE for standardization in 1986, and the language was standardized by IEEE in the year 1987. Now this version of the language is now known as the IEEE standard 1076-1987. This is the language that we are currently using, and it's now an IEEE standard. Now, this language has a capability, as I just mentioned, the purpose of standardizing the language was so that it can be used in exchange medium between the chip vendors and the CAD tool users. So the language has become platform independent and it has become a medium of exchanging technologies, of exchanging the designs between different designers and the chip vendors who are actually going to be fabricating these chips for these designers or the CAD tool users. Now the language also supports hierarchy. That means the language can be modeled as a set of interconnected components, and wherein each component can then be modeled as an interconnection of further sub-components. As I mentioned before, the language supports two design methodologies, the top down wherein we begin from the system, move on to the subparts till we come to the gate level, and the bottom up wherein we begin from the gate level, move on to the circuit level, and finally the system. In between a subsystem is also possible. So the hierarchy can be maintained, and as many levels of sophistication, as many levels of abstraction can be added as the designer deems fit. Now, as I mentioned earlier, the language is not technology specific. That is, it is not dependent on a certain target technology, but it is independent. So, it is capable of supporting technology specific features. So, whichever technology, target technology it is going to be implemented eventually in, the language can be easily ported into that particular technology. It can also support various hardware technologies. For example, one may define new logic levels, new components. You may also specify technology specific attributes. So, a lot of flexibility to the designer, to the programmer has been provided by this language, whereby the programmer can introduce his or her new logic types. So, this is also something which is very supportive of the new research in the area, whereby the researchers or the scientists are able to introduce their own parameters, their own attributes, and the language very well supports these new technologies. Now, by being technology independent, we understand that the same behavior model can be synthesized into different vendor libraries. There are different vendors which are having their own libraries. For example, there is a UMC library, and then there is a TSMC library. So, these libraries are there, they have their own individual attributes, but VHDL being a technology independent can be very well integrated into any of these libraries. Then it supports both synchronous and asynchronous timing models. So, all type of digital designing can very well be accommodated using VHDL. Now, various digital modeling techniques such as finite state machines, that is the FSM descriptions, the algorithmic descriptions, and the Boolean equations all can be modeled using this language. As I mentioned earlier, it is an IEEE standard, and it is also the ANSI standard now. Therefore, models described using this language are portable. The language supports three basic description styles: a structural, a data flow, and behavioral. The structural and behavioral I have already mentioned. Data flow simply defines the data between the signals, that is from input to the output, or intermediate nodes if any. We will discuss it in detail as I move forward towards these styles. And there is a mixed style modeling also supported by VHDL, wherein all three of these techniques or any two of these can be integrated to develop one particular hardware description. Then, as I mentioned before, it supports a lot of abstraction levels ranging from the behavior of the description, the behavioral description, to very precise gate level descriptions. It does not support modeling below the transistor level. That means the maximum I can begin from is the gate level and forward. Now, arbitrary large designs can be modeled. There is no limitation to the number of gates that can be modeled. So, as many bigger design as is possible can be very easily written using the VHDL. However, for an efficient design, it is always better to break down the large design into different modules, and the modules can later be designed using HDL. However, for large designs, the support from the VHDL is available. Now, nominal propagation delays, the minimum and maximum, oftenly called the min-max delays, the setup and hold timings, the timing constraints, and the spike detection. All of these attributes can be described very naturally in this language. A provision is also there to not only describe the functionality of a design, but also contains information of the design itself in terms of user-defined attributes. For example, the total area and the speed of the circuit. Once the simulation has been complete, we get all these results, wherein total area eventually that will be occupied by the IC once developed, and the speed in terms of the propagation delay of the entire circuit is also available. Now, the capability of defining new data types is a very important feature of VHDL, wherein a user can introduce his or her own defined data type into the language, and that can also be supported and can be used to simulate a design technique at a very high level of abstraction without any concern about the implementation details. Now, when organizing a VHDL design, there are a few parameters, essentially 5 parameters that are to be considered. First one being the entity, which indicates the symbol, can be considered as a black box, wherein some input connections are coming and some output connections are going. These inputs and outputs are referred to as ports. Now after this gives us the external view basically of the circuit under consideration. For example, if I am talking about a half adder, so without bothering what is inside, what gates are the comprising of this half adder, I just assume it to be a black box and I simply define input and output ports, wherein input ports will be the numbers to be added, say A and B, and output ports are the outputs expected out of this black box once it has worked as a half adder, which will be sum and carry. The next is the architecture. Now this is the internal view of this particular entity. So this is going to give me one of the several implementations of the design. A design can have more than one type of architecture. An architecture that can be based on the structural approach, an architecture can be made out of the behavioral approach and so on. So for one entity, multiple architectures are possible. Then a configuration. Now since as I mentioned that multiple architectures are possible, then which particular architecture is going to be binding with that entity under what consideration is defined by the configuration. So it indicates the binding between the symbol and one of its many implementations, that is one of its many architectures, and it can also be used to express the hierarchy being followed in the circuit. Then the libraries, these are the logical units that are mapped to the physical directories. The units of libraries are called packages. So packages are basically the repositories of the type definitions, procedures and functions which are predefined, and they can also be user defined. A user can declare his or her own package, and certain packages are already inbuilt in the libraries that are provided with the VHDL system. So a package essentially comprises of two parts. There is a package declaration which specifies the package contents, and there is a package body which introduces the code blocks for those contents for which the declaration has been given. Now this particular diagram shows there is this device which is the actual hardware and the VHDL view wherein the device has been broken down into these different entities, and for each entity there is a device model associated with it which has been described. Now coming to the entity, entity is basically a hardware abstraction of the hardware device. It is described using one model that contains one external view and one or more internal views. And at the same time, a hardware device may be represented by one or more entities. An entity is modeled using an entity declaration and at least one architecture body. It may have more than one architecture body, but at least one body will be associated with it. So the entity declaration basically is going to be describing the external view of the entity which is being described using the HDL. Now the architecture body contains the internal description of the entity which has been described. The configuration declaration is used to create a configuration for an entity which specifies the binding of one architecture body from the many bodies that can be associated with that particular entity. It can also specify the bindings of components used in the selected architecture body to the other entities. An entity may have a number of different configurations, and based upon the number of specifications of the architectures, that many configurations can be made. Further, a package declaration will be encapsulating a set of related declarations such as type declarations, subtype declarations and subprogram declarations that can be shared across two or more design units. And a package body contains the definitions of the subprograms that are declared in the package declaration. So every package declaration must have a package body wherein the declarations have been elaborated upon. Now once an entity has been modeled, it needs to be validated by a VHDL system. A typical VHDL system comprises of an analyzer and a simulator. Now what does an analyzer do? It reads in one or more design units contained in a single file, compiles them into a design library after validating the syntax and performing some static semantic checks. So it is basically just an editor kind of a function it is doing. It is going to edit, see whether everything is syntactically and semantically correct without going into the technical details. The design library is then placed in the host environment, that is the environment that is going to be supporting this VHDL system, where the compiled design units are stored. Now coming to an entity declaration, let's see with the help of an example. As I mentioned earlier, the entity declaration will be specifying the name of the entity being modeled and list the set of interface ports. Now this is an example wherein a mux has been given comprising of three input lines A, B and S and an output which is F. So I define an entity mux and I say entity mux is A, B and C are input ports of bit type and F is the output port of bit type, and we finally end the entity by saying end mux, and ports are the signals which are going to be communicating in the entity to the outside world. Thank you. Moving on with the description of an entity of a particular VHDL program, let's consider an example of a half adder, wherein a half adder comprises of two input signals A and B and two output signals sum and carry. Now, when describing the entity, I am not concerned about what is inside the circuit, that is the XOR gate and the AND gate is of no concern to me while just I am designing the entity. So, I use the keyword entity, give a name to this entity like I have given a half underscore adder, any name can be given depending upon the user requirement, followed by the keyword is. So, entity half adder is, then I use the keyword port. Now, this keyword port indicates the input and output ports, wherein I define all the ports which are going to be getting the input from the outside world and delivering the output to the outside world. So, as I can see, there are two ports A and B which are of type in, specified by keyword in, of type bit. Now, bit indicates that these ports can have a value of 0 and 1. Besides that, there are other types of ports also which we will cover as we move forward in our discussion of the architecture body and entity declarations. Then there is S and C which indicates the output bits. Again, type out, that is, it is going to be giving me the output to the outside world, and again the output S and C will be of type bit, that is, it can have a value 0 or 1. Then I end my entity by saying end half underscore adder, which is the name of the entity. So, the entity that has once been initiated has to end by using the keyword end followed by the name of the entity. Now, coming over to the architecture body. Now, architecture, as I mentioned earlier, gives the internal details of an entity. That means the black box that we were considering, like when I was discussing the half adder, now what is inside that black box is dealt with by this particular architecture body. So, the architecture body will be specified, and one of the following methods, that is a structural modeling, a data flow modeling, a behavioral modeling, or a mixed style of modeling will be used to describe this architecture body. It is important to mention here that the entity description is independent of either of the modeling styles. It will be written in the same fashion even if any of the modeling styles is adopted, but architecture will depend upon the modeling style that is being used. Accordingly, the semantics will change, which we will see as we see more examples down the line. Now, first type of modeling is the structural modeling, which is basically a set of interconnected components, that is, it is going to be representing the physical structure. The data flow modeling, which will be a set of concurrent statements to represent the flow of data, and the statements will be executed in the concurrent fashion, so they can be written in any order. Then next is the behavioral modeling, which is a set of sequential assignment statements. So, they are going to be representing the behavior and also going to be specifying what is happening after what. So, a sequence is to be followed. So, whatever sequence the circuit is going to adapt, the statements in this particular style of modeling have to be written in that particular sequence itself. Then finally, a combination of any of these three can be used, which is known as the mixed modeling style. Now, as can be seen in this particular block diagram, there is an entity. The entity can have one or more architectures. So, these architectures can be a data flow type of architecture, a behavioral type of architecture, a structural architecture, or a hybrid, which is a mixed signal architecture, a mixed model which is comprising of any of these three combined with the other or all three of them together. So, the entity can be described in either fashion, and if multiple architectures are given, then declaring a configuration becomes a mandatory requirement to indicate under what particular consideration or under which case which of the architecture body is to be used. Now, let us focus on the structural modeling and see with the help of an example how the architecture is written using this particular approach. For the sake of simplicity, I am going to be discussing about the half adder itself, because the structure being simple, it is easier to understand. So, as I mentioned earlier, that essentially the structural style of modeling is defining the entity in terms of the interconnection of components. Now, we know for a half adder, the components that are required are an XOR gate and an AND gate. So, how I start writing an architecture is I give a name to this particular architecture. So, I say architecture, for example, HA underscore structure. I can give any name. I can say half add, I can say H add, or whatever is the user requirement of half adder. Half adder is now the name of the entity that I have declared. Now I describe the components. There is a component XOR 2. XOR is there since it's a 2 input XOR, so I say XOR 2. For a 3 input, it will be XOR 3, and for a generic, I will say it's XOR n, wherein n number of inputs are there, which can then later be defined what is the value of n. Now, this XOR is a 2-bit port, 2 input XOR, so I say port X and Y. Now, here X and Y are arbitrary names I have given to a generic XOR gate. I am not putting my A and B directly here, because here I am in general describing a component XOR. So, I say X and Y, which are of input type bit and an output Z of type bit. Then AND component. Then I say component AND2, which is an AND gate, which is a 2 input AND gate. I give it 2 ports L and M, in bit and N output, and I end my component. Then I actually begin writing the code for my particular circuit, which is my half adder. So, I say begin. Now, this next statement indicates x1 colon XOR2. Now, x1 is an instance of XOR2 component that has been declared in my architecture earlier. So, wherein by this x1, I am going to actually pass on the actual signals that are to be applied to this particular XOR gate. So, in order to do that, I introduce a keyword called as port map, whereby I am mapping the ports of the XOR gate to my actual input signals. So, what I do is I simply say A, B, sum. Here, positional association comes into picture, wherein A becomes associated to X, B becomes associated to Y, and sum becomes associated to Z. So, it is very important to keep in mind here that I cannot change the order, because this is going to be positional association. If I change the order to A, sum, B, then what will happen? A will become X and sum will become the second input Y and B will become the output Z. So, positional association has to be taken care of, and accordingly the signals have to be defined. Now, here it is important to mention also that A, B and sum have already been declared as input and output bit types in their entity. So, they need not be again mentioned here, need not be again defined here, they can be directly used. Whereas, for the case of X, Y, Z and L, M and N, since they were not defined earlier and they were arbitrary values associated with my component, they have been described in the architecture body. Now, similar to x1, I introduce an instance of component AND2 and I give it a name A1. Now, again X or A have not been purposely used to indicate XOR or AND gate. Any alphabet can be used to give the nomenclature of this particular gate. So, and as many number of instances that you are going to be creating, those many numbers of alphabets will be required. For example, had I been requiring 2 XOR gates, I would have created 2 instances x1 and x2. Similarly, for the AND gate. So, now again for AND gate I have declared A1 which is an instance of AND2 and mapped the ports by using the keyword port map with A, B and carry. That means A becomes L, B becomes M and carry becomes n. So, I am going to be getting carry equal to A and B, similarly sum equal to A XOR B. And finally, I end my architecture by saying end HA underscore structure. Now, as I had mentioned earlier when discussing about VHDL, that the language is a little verbose. So, initially it is a little difficult to remember all the modalities of the language, but once we become habitual of writing the code, then this all becomes very, very easy to remember and implement. Now, moving on to the second type of modeling, which is the data flow modeling. Now, as I mentioned earlier, it is just indicating how the data is flowing between the input and output signals or any intermediate signals or variables, if any. So, in this style of modeling, the flow of data through the entity is expressed using concurrent signal assignment statements. So, the main difference between data flow and structural is that the statements will be concurrent. So, accordingly, it is the wisdom of the designer to choose which kind of style of modeling is more suited for his particular structure. So, if the structure allows for concurrent execution of statements where the order does not matter, then the data flow modeling can be very easily employed. So, the structure of entity is not explicitly specified in this model. So, we have nothing to do with the structure here, but it can be implicitly deduced. By the functionality that is being implemented, we can automatically deduce that what must be the structure of this particular circuit. Now, for an example, again for the half adder, a description has been given using the architectural description using the data flow style of modeling. So, architecture HA underscore concurrent, I have written as underscore concurrent. For data flow programming itself, the entity name and the architecture name can be same, but it cannot be for any other styles of modeling. So, but for the sake of ease, what we do is we prefer that the architecture name be taken independent or different from the entity name. So, we begin with the keyword begin, then sum and carry are the two output signals that are to be generated. So, I simply say sum equal to, this is the symbol that is used for assigning a value to a signal, equal to A XOR B after 8 nanoseconds, and carry is A and B after 4 nanoseconds. Then finally end the name of the architecture. Now, concurrent statements can be are mentioned actually as concurrent because they can be executed in any order. So, therefore, ordering is not important. But as you can see in this example, the after statement has been introduced. So, this is going to be telling me that if I begin my simulation at time t, then carry will be getting its value at time t plus 4 nanoseconds and sum will be getting its value at time t plus 8 nanoseconds. So, the signal assignment statement, the symbol implies the assignment of value to a signal. That means the target which is on the left hand side is a signal type. So, the value of expression on the right hand side is computed and assigned to the target signal, that is the left hand side. A concurrent signal assignment statement is executed only when any signal used in the expression on the RHS has an event on that value and the value of the signal changes. That means, coming back to this example, sum is equal to A XOR B. Now, this statement will be executed if and only if some change in the value of A or B or both occurs, then only this statement will be executed. So, the execution will be a consequence of change in the signal, change in the input signal, else this will not be executed. Now, delay information has been included in these signal assignment statements using the after clauses. So, if either signal A or B, which are the input signals to the half adder entity, have an event say at time t, then right hand sides of both signal statements are evaluated. Signal sum will be scheduled to get a new value after 8 nanoseconds, while signal carry will be getting the value after 4 nanoseconds. So, as I mentioned earlier, the statement will be executed only if an event occurs, and beginning from that time, the values of the finally the target signals will be assigned. Now, concurrent signal assignment statements are executed concurrently, and thus again their ordering is not important. This totally contradicts or contrasts it from the behavioral type of programming, which we will just see as we move forward. Now, coming to behavioral style of modeling, it is used to specify the behavior of an entity as a set of statements that are executed sequentially in a specific order. Now this set of sequential statements that are specified inside a process statement, they do not explicitly specify the structure as in the case of the data flow modeling, but it specifies the functionality. And similar to the data flow modeling, once we see the functionality, then the architecture, the structural description can also be deduced from the same. Now the process statement, which is a distinguishing feature of the behavioral modeling, is a concurrent statement that can appear within an architecture, and the block of statements contained within this process statements are sequential statements. Now as an example, for again the half adder, the architecture H_adder of half adder is begin process A comma B. Now process A comma B, a process is the keyword which indicates that what follows next is a process which is sequential in nature, and that this process is sensitive to changes on A and B. So the list in the parenthesis after process is called as the sensitivity list. So that means the signal A and B are what makes this particular set of statements in the process statement as sensitive. If any change occurs on either A or B, the statements that follow will be executed. Similar to what we had in case of data flow, wherein for concurrent statement, each statement had to be executed based upon the function occurring on the RHS. Whereas in case of the process statement, if the change occurs on either of the signals in this parenthesis, then the entire set will be executed following from begin. So we can see process A comma B, begin, S equal to A XOR B, C equal to A and B. Now once the execution starts, the simulation starts, first statement to be executed will be S equal to A XOR B, and the second statement will be C equal to A and B, because this is a sequential type of programming. So obviously the sequence will be followed, sum followed by the carry. Then since we have begun a process, so we end a process, and since we have begun an architecture, so we end the architecture also. Here it is not mandatory to give the name of the architecture, only end semicolon also suffices. Alternatively, we can also mention as end H_adder, which will mean the end of the architecture. Now it is very important here to get into a little depth of what this process statement is capable of doing and what is the physical significance of having this statement. Now process statement has two parts, a declarative part which is placed between the keywords process and begin, and a statement part which is between the keywords begin and the end process. Now statements appearing within the statement part and the sequential statements are executed sequentially like I just mentioned, and the list of signals specified within the parenthesis after the keyword process constitutes the sensitivity list, and the process statements is invoked whenever there is an event on any of the signals in this particular sensitivity list. So signal assignment statements appearing within the process are called sequential signal assignment statements. So sequential signal assignment statements, which includes the variable assignment statements, are executed sequentially independent of whether an event occurs on any signal in the right hand side expression or not. They are totally dependent upon the sensitivity list in the process statement, unlike what was the case in the data flow wherein it was dependent on any action occurring on the RHS. So here it is not dependent on that. If any change occurs in anything which is contained in the sensitivity list of the process statement, the remaining statements will be executed. As an example, we may consider a flip-flop over here. Say a D flip-flop is there. Now for a D flip-flop, we know that there is an input D. Besides that, there is a clock signal. Now this particular D flip-flop is sensitive to clock. So the sensitivity list, when we write the behavioral description for D flip-flop, will comprise of the clock. So any time an event occurs on clock, the output Q will be assigned the value D. So it will not wait for anything to happen on D, instead it is sensitive to clock. So that is why we say that in behavioral programming, the sensitivity list is what determines the execution, unlike data flow wherein the right hand side of the signal assignment statement determines the execution sequence. Now sometimes it may happen that I may have a process which may not have a sensitivity list. So it can be used, we can use an explicit wait statements that can be used to suspend a process. It can be used to wait for a certain amount of time, or to wait until a certain condition becomes true, or to wait until an event occurs on one or more signals. For example, if we see here, we've defined a process, there is no sensitivity list, we begin and we say that clock is 0 for, and then we wait for 20 nanoseconds. We don't do anything. So as can seen in the output that initially from 0 to 20 the clock stays 0. Then after 20 nanoseconds what happens? The next executed statement is clock is 1 and we wait for 12 nanoseconds and then end process. So what will happen? This particular clock signal will go on getting generated with an off period of 20 nanoseconds, an on period of 12 nanoseconds, again followed by an off period of 20 nanoseconds and so on. So a process without a sensitivity list is also possible provided that we have given a wait statement in the process description. Now a few points about the process. A process never terminates. It is always either being executed or is in a temporarily suspended state. Now what does that mean? That once, for example, for a half adder where we say process is sensitive to A comma B, if an event occurs on A, then what happens? The statements are executed and then this process is said to be in executed state, being executed state. Now once that complete execution has been done, the process will be suspended and it will keep on waiting on the sensitivity list for some other change to occur in either A or B. As soon as the next change occurs, it gets executed. So all the processes are executed at least once during the initialization phase of simulation until they get suspended. Therefore, a process with no sensitivity list and with no explicit wait statement will never suspend itself. It will go into the infinite loop and it is not going to be suspended. Now having discussed the three styles of modeling, next style of modeling is the mixed style of modeling. Now in this modeling it is possible to mix the three modeling styles together that we have seen so far in a single architecture body, or either of the two can also be implemented. That is, within an architecture body we could use component instantiation statements that represent the structure, the concurrent assignment statements that represent the data flow, and the behavioral process statement that it represents the behavior of the entity under consideration. As an example, we have taken a 1-bit full adder. Now this is going to be having 3 inputs which are going to be passing through 2 XOR gates and 3 NAND gates to generate the sum and the carry. Now we will be first defining an entity which is a full adder in this case. So port A, B and C in of type in and sum and C out of type out bit and end full adder. As I mentioned earlier, irrespective of the style of modeling we are using, the entity description and declaration will not change. Now then I define the architecture. I give a name FA underscore mixed for full adder is. Now here component XOR2, the components that are being called, XOR gate is being called twice, but component declaration has to be done only once. It can be later called on twice by introducing 2 instances like I mentioned before. And then if you can see intermediately, first XOR is producing an output which is going into the second XOR. So this output of first XOR can be defined as a variable or a signal. Difference between variable and signal we will be seeing as we move forward. So herein we have declared a signal S1 which is of type bit. So essentially S1 is giving me A XOR B. Then I begin wherein I say XOR X1 is equal to XOR2 port map A, B and S1. So simply AB XOR S1 is the output that is giving me. Then I begin my behavioral description wherein I define a process which is sensitive to A, B and C in. I define 3 variables T1, T2 and T3. These are essentially the outputs of 3 NAND gates that have been put in here. Then followed by that I say begin T1. Now here it is important to note the symbol that is being used for the assignment of value to a variable. It is a colon equal to as opposed to the symbol used for signal declaration which was the symbol used for less than and equal to. So T1, T2 and T3 are defined as A and B, B and C in and T3 as A and C in. Finally, C out is the ORing of T1, T2 and T3. So C out is T1 or T2 or T3 and finally end process. So now what I have done is that by using structural programming, I have determined the value of S1. Using behavioral programming, I have calculated C out and finally I am going to be calculating sum which will be given by S1 XOR C in. And finally, I am going to be ending my program saying sum end the name of the architecture. So this simply indicates that the process has been used for the carry generation, the data flow programming has been used for the final sum generation, and the structural has been used for describing the calculation of first XOR, that is A XOR B. Now alternatively, as this has been used, this particular program has been given here to show the usage of 3 styles of programming. It is always preferable that structural programming be used wherein one component is being repetitively used. For example, here XOR gate has been used twice, so one could have easily called this twice, one to generate the first output and second to generate the second output. So I could have created 2 instances, x1 XOR 2 port map AB S1 and x2 XOR 2 port map, then the second will be S1 Cin and sum. So the last statement of calculating the sum using data flow could have been easily removed. Now, what are the different types of VHDL objects that are defined? They are essentially constants, variables, signals and files. Now, most of these terms we are already familiar with in other types of programming languages, but their definitions differ a little when we come to VHDL descriptions. Now, a constant is a one whose value once assigned cannot be changed. So, this is true for any of the programming language, that a constant has once been defined. For example, I say that time t is equal to 10 nanoseconds, and once that has been defined, this cannot be changed. So, throughout the execution of the program, t will be having a value of 10 nanoseconds only. So, the benefits of this is it's a better documented design, and it is easier to update design because the constant is always same. Then there are signals. It is a physical signal, that means it can be considered to be a piece of wire, and it is a sequence of time value pairs. That means a particular value is going to be generated at a particular time. So, a signal assignment statement takes effect only after a certain delay, which is the smallest possible delay, called as the delta delay. It is possible to define global signals that can be shared among entities, but more often signals are just locally defined for a given architecture. And now variables are assignments to variables are scheduled immediately. That means the assignment takes immediate effect, contrary to what happened in signals, wherein we waited for a particular delay, which is the delta delay. A variable takes the value instantly. So, if a variable is assigned a value, the corresponding location in the memory is written with the new value while destroying the old value. So, the old value that was assigned to that particular variable or that variable acquired is overwritten by this particular new value. So, this effectively happens immediately. So, if the next executing statement in the program uses the value of the variable, it will be using the new value because the old value has been overwritten. So, typically variables are used for local storage mechanisms and are visible only inside the process as opposed to the signals which can be globally visible. The coming to signals versus variables, signal assignment statements are scheduled after a certain delay, that is the delta delay, and variable assignment statements happen immediately, so there is no delay. So, choosing between declaring a particular type of an intermediate signal as a signal or a variable becomes a very sensitive issue, considering these two aspects of the delta delay and the immediate assignment as in the case of a variable. Now, as I was mentioning that the port type that we have seen so far is the in and out type. Besides that, there are certain other types of ports that can also be used while defining an entity. So, in port is there, which is the value of the input port can only be read within the entity. Out stands for the fact that the value can be read out or can be updated within the entity model, but it cannot be read. That means it can only be written into. Third type is an in-out. So, this type of value is a bidirectional port. That means you can read from it and write into it. So, any signals that are bidirectional signals, for example, those used in case of feedbacks can be declared as input-output type. Another type is the buffer. The value to be read and updated within the entity model. However, it differs from the input mode because it has the capability of storing also, and it cannot have more than one source. It can be only taken from one source, and it can be also connected only to a buffer type only and at most to one source. So, based upon the requirement of a particular program or a particular circuit, these can be updated, the port types, besides the in and out, the regular in-out, buffer and modes can also be used. Now, besides this, it is important again to mention that there are certain programs wherein, for example, I am defining a multiplexer, then the vectors can also be defined using these data types. Thank you so much.
Dear friends, we hope that with today's lecture you have come to understand what various hardware description languages can be, and on that note we would like to thank Ms. Bhatia for this wonderful lecture, and thank you dear friends for watching our show. Stay tuned and keep watching. Thank you.